Hello everyone, I'm Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course Operating Systems. We are in the process of learning about process synchronization. I hope you all have watched the previous videos. In our previous videos, we have learned about what is the need of process synchronization, whereas part of that we understood if there is no synchronization while multiprocessing they are performing their task, then they may lead to race condition because of the shared resources. So to avoid that problem, which is a critical section problem, we have understood in detail what is critical section and what are all the different types of solutions we have for the critical section problem. Mainly, we have two categories, software solution and hardware solution. In our previous videos, we have learned in detail about these two solutions. Software solution is Peterson solution, which is having a disadvantage of connecting that one to only two process. To solve that one, we have hardware solutions, which are test and set instruction, and the second one is swap instruction. I hope you all have gone through those videos and understood in detail how they are working. All right. So, with the knowledge of hardware-based solutions, where we could able to achieve mutual exclusion, progress, bounded weight with the test and set instruction, and also swap instruction also helps us in achieving the mutual exclusion. But in real time, like for application programmers, if they want to use, it will be complicated for them if they use this hardware based solutions. I'll revise. Hardware based solutions are complicated for, or hardware based solutions are inaccessible for application programmers to use. So what happened? The designers have developed a higher level solution tools like the one which it is reflected here, semaphores, to solve the critical section problem. So Semaphore is a higher level software tool. Make a note, all of you. Because the hardware tools are very difficult to use by the application programs which we are developing, so that we can make use of these higher level software tools Semaphore. So this is a higher level software tool. Which helps us in resolving this critical section problem. Now, one thing you need to understand is this semaphores is mainly used to achieve mutual exclusion only. Critical section problem requires three requirements to be satisfied like mutual exclusion, progress, bounded weight, right? But if you're going with this higher level solution, then the semaphores will be mainly used to achieve the mutual exclusions. So keep your note down that point also. This is mainly used to achieve mutual exclusion. Where you all are aware what is nothing but mutual exclusion. Mutual exclusion is nothing but if one process is in the critical section area, then other process is not allowed to enter into the critical section. It has to wait. So keeping these two points in in our mind, let us understand what is this semaphore and how it can be used. So the definition of a semaphore is the semaphore is an integer variable and it can be shared by multiple processes. Very simple. Semaphore is an integer variable which can be accessed by multiple processes. Note down the definition, all of you. Semaphore is an integer variable which is shared by multiple processes. Now, as it is told like it is an integer variable, obviously it has to be initialized. So, semaphore can be initialized. It can be initialized and it can be accessed by only two methods only. Semaphore can be initialized, but after initialization or to work with this semaphore can be accessed by only two standard operations. The semaphore variable can be accessed by only two standard, which are atomic operations. They are wait and the other one is signal. So only these two functions can use this semaphore. Generally, semaphore is represented with a variable name like S, capital S, and this S variable can be initialized and that variable can be used by two operations only, that is signal wait operations. Now what do you mean by atomic operations? Atomic operation is nothing but this wait may be having some lines of code. This wait function may be having some lines of code. Those lines of code will be executed continuously without any interrupt. I'll tell you once again. Suppose if you have a wait operation, now may have this wait function may have some lines of code, right? These lines of code once started, it has to complete all the lines of code. It should not be interrupted. That means it doesn't mean like after executing this one line of code, CPU can go somewhere and it can execute that statement. No, it should not happen. Once a wait function has been called, all the lines of code in the wait and all the lines of code in the signal operation needs to be executed. If wait is called, all the lines of this state function should be executed without any interrupt. So that's why they are called as atomic operations. Understood? So these operations are atomic operations. So how wait and signal are defined? Let us see the code for this one. Make a note of this wait and signal code and we will understand how they will be working. So the wait is written like this. I will write down here wait. Wait has been defined like this. And it takes a variable called yes. And then it is having a line of code where it will check while the variable value of s is less than or equal to 0. If it is less than or equal to 0, then it has to do nothing. But if the variable is greater than 0, then it has to decrement the value of s by 1 and then it has to come out of this function. The operation is very simple. It will get a variable value s and this s value is to be compared with 0. If it is less than or equal to 0, it has to do nothing. So for your understanding, I'll add one comment line also here. So it has to do nothing if it is true. I hope you all are clear with this simple wait. Wait will take a variable whose value, if it is less than or equal to 0, then it will do nothing. If the condition is false, it will come down and it will decrement the value of s by 1. S minus minus operation will be done. This is our wait. Now note down signal operation. Signal will also take a variable called yes as a parameter, and whenever signal function is called, it does only one operation where it will increment the s value by 1. That's it. So whenever you call the signal operation, it takes that value and increment its value by 1. Only one line of code for the signal. So these are the two atomic operations, which are signal and wait, which will be used by the semaphore variable. And these two are atomic operations. and semaphore can be accessed by these two variables only. Right. Now, generally, I hope you all are clear with these two functions. Okay. Now, semaphores are of two types. Note down what are those two types. Semaphores are of two types. Two types. First type is counting semaphore, and the second type is binary semaphore. Semaphores, which is an integer variable, is of two types: counting semaphore or a binary semaphore. Counting semaphore is nothing but the value of this semaphore may range to an unrestricted domain. That means the value may start from 0, 1, and it goes on to 1, 2, 3, 4, 5, like that. So this semaphore value, generally it is initialized to the number of resources available. So make a note of that one. Semaphore, counting semaphore. This semaphore is generally initialized to the number of resources available. Suppose if you have 5 resources, then the semaphore value will be 5. And its value can be range over an unrestricted domain. That means there is no limit on the value for this counting semaphore. Whereas coming to the binary semaphores are of like this value range between 0 and 1 only. As the name told, binary semaphore, it will range between only 1, range between 0 and 1 only. Its value can be 1 or its value can be 0. Right. So these are the two semaphores that we have. Counting semaphore, whose values can start from 0 to unlimited value. Whereas coming to the binary semaphore, its value can be 0 or 1. These binary semaphores are also called as mutex lock. These are also referred as mutex locks. Generally, to achieve mutual exclusion, we will be using these binary semaphores to achieve our mutual exclusion. Generally, in our like if in your future discussion, we will be using this binary semaphore to achieve the mutual exclusion. All right. Okay. Now let us understand how they have defined using this binary semaphore, how the mutual exclusion can be achieved. So the code is very simple. The code is like this. You need to have a statement between do and while, because any process wants to use the critical section. Now, any process, if they want to use the critical section, the first thing they need to execute is they need to call the wait function with a mutex value. Mutex value, always remember, the mutex value is initialized to 1. The range may be between 0 or 1, but the variable mutex is initialized to a value of 1 always. Okay, that value mutex is shared between multiple processes. Okay, so the wait value has to be executed, and then after executing the wait value, they have to end with a semicolon. After that, after wait, they have to enter into the critical section. Any process can enter into the critical section. After entering into the critical section, they have to execute the signal process. Signal function with a variable of mutex. Okay, how it is working, let us understand. This is the simple code that has been taken. How the way the process has to go into the critical section by using the wait and signal to achieve this mutual exclusion. Here mutex is your semaphore variable. Let us consider two process P0 and P1. Okay, P0 and P1. Suppose P0 wants to enter into the critical section. Okay, so P0 has started entering into the critical section. Now P0 is here. P0 has started its execution. P0 is here. Now after executing this statement, what happens? It is calling weight of mutex of 1. So mutex is value is what? 1. Right. Now mutex is shared by P0 and P1 both. Mutex value initially is 1. P0 is executing weight of mutex. So you will come here. So S value will be here. 1 value will be copied. Right. And then while S value is 1 is less than or equal to 0, which is false. So it will come here and it will decrement the S value. So S value is 0. That means the mutex value has been changed to 0. Right. After executing this one, it has come here, come out of this while wait, and it has come to here, and after that P naught enters into the critical section. Got it. Now P naught is in the critical section. Let us consider P1 also wants to enter into the critical section. It will start executing this statement. It will call weight of mutex. Mutex value is now 0. It will send here S value of P1 is 0 now. Now S value 0 is less than or equal to 0, which is true. So the condition is true. So now P1 will be in this loop continuously. It will not come out of this loop. Now P1 has struck here because P0 is in the critical section. So that is what we want to achieve. Mutual exclusion has been achieved. As P0 is in the critical section, P1 has been blocked here in the wait. Right. Now P1 has completed its work with the critical section. It has come here and it is executing the signal. Now what is the signal? Signal of mutex. What is its value? 0. So S value is 0 here. We are incrementing the semaphore value by 1. That means S value, which is 0, has been incremented by 1. That means 1. That means the mutex value has been changed to 1. So after executing this statement, P0 will come from here to here and it will come out of this loop. Now P0 is not in the critical section. Now P1, which is waiting here in this loop, it will check the S value. What is the S value? We got the semaphore value as 1. So 1 is less than or equal to 0, which is false. So it will come out of this loop and it does S value as 1. That means the mutex value has been reduced to 0. And after coming from here, P1, what happens? It can come here and it can enter into the critical section. So successfully, by using a simple approach of semaphores, by using this binary semaphore, we could able to achieve the mutual exclusion, where one process, if it is in the critical section, we can block the other process entering into the critical section. I hope you all are clear with the simple example, like simple introduction to the semaphores concept. What is semaphore and what are all the two methods that can be accessed by the semaphore and what types of semaphores are there and how the flow of execution is defined. From the next class onwards, we will be understanding some classical problems of synchronization like bounded buffer, which is producer consumer problem, readers writers problem, and dining philosophers problem, where all the solutions to these problems is solved by using semaphores concept. With this, we come to an end of today's lecture. Let us all meet in the next lecture. Until then, thank you all of you.